Welcome back to the deep dive. We spend a massive amount of time talking about what AI actually does, right? Like it
Yeah.
writes code, it generates these surreal videos, it scares the living daylights out of policymakers.
Right. Yeah, it definitely does.
But we rarely talk about what it actually is.
It's
Like
just
what?
structurally.
Exactly. I mean, if you ask the average person on the street to just visualize AI, they usually picture, I don't know, a glowing blue brain floating in a server room somewhere. Just this singular magical entity.
The classic black box myth.
Yeah, the black box, yeah.
But I've been reading this really comprehensive review paper published late in 2025. It's by Wei, Wang, and Watada, and it's called A Modular Perspective on the Evolution of Deep Learning, Paradigm Shifts and Contributions to AI. And honestly, it completely kills that magic brain metaphor.
It really does. It replaces it with something that is much more pragmatic. Legos.
Legos.
Exactly.
Yeah.
The whole mission of our deep dive today is to unpack this. Because the core thesis here is that we didn't get to these massive models like GPT-4 or Sora by just building a bigger, better brain. We got there by inventing better blocks.
Right. Interchangeable, standardized modules.
Yeah, that we could just stack in different ways to build these absolute skyscrapers of computation.
And that distinction really matters for you, the listener, because when you stop looking for magic and you start looking at the actual modules, you realize that modern AI is really just extreme engineering.
It's mechanical.
It is. It's about figuring out which blocks snap together without the whole tower toppling over.
So that is the plan. We are going to dump out the Lego box. We're going to look at the specific blocks that power computer vision, the blocks that power language.
Like the famous attention mechanism.
Right, exactly.
Oh.
And then we'll look at some of the really weird cutting-edge designs that might actually replace our current tech stack entirely.
Sounds good. Let's get into it. Let's start with the history, because the paper makes a strong point that this modular approach wasn't always the default. Like back in the 50s and 60s with Newell and Simon's logic theorist, or early knowledge systems like Dendrildal, were they trying to build modules then?
No, not really. The early days were heavily focused on mimicking biology directly. Take Rosenblatt's perceptron, which is essentially the grandfather of neural nets, or Hopfield networks later on. They were designed to act like a single biological neuron.
Right, it takes an input, weighs it, and fires.
Exactly. But it was entirely linear.
And linear is a pretty big limitation.
Extremely limited. A linear model is basically like trying to draw a realistic portrait using only a straight ruler.
You just can't capture the curves or the complexity.
Right. You can't even tell if a cat is a cat if the photo is slightly rotated.
Yeah.
And for decades, the field was just stuck. They couldn't figure out how to stack these artificial neurons deeply without the underlying math completely breaking down.
But then the paper identifies this sort of big bang of modularity right around 2012. AlexNet.
Yeah, AlexNet changed everything. That was the exact moment researchers realized, hey, we don't actually need to simulate a human brain perfectly. We just need to stack specific, standardized operations.
Like convolution, pooling, activation layers.
Exactly. You stack them like a sandwich. And by doing that, AlexNet completely crushed the ImageNet competition. It proved the modular concept worked.
But there was still a ceiling even then. The paper talks extensively about the vanishing gradient problem.
Right, the vanishing gradient. Think of this as the ultimate game of telephone. When you train a neural network, you pass data forward through the layers, you check the error at the very end, and then you send a correction signal backward to update all the weights.
To tell it what it did wrong.
Right. But if the network is too deep...
Like if there are too many layers.
Exactly. The correction signal just fades out before it ever reaches the beginning of the network. The early layers never learn anything at all. So you were effectively capped at maybe 20 or 30 layers.
Which brings us to the first superblock mentioned in the text, ResNet.
The residual network. This is arguably the most important engineering fix in the entire history of deep learning. ResNet introduced something called a skip connection.
I love this concept so much. It's basically just a shortcut.
It is. Think of it like an express elevator in a skyscraper. The signal doesn't have to stop at every single floor. It can completely bypass a whole block of layers and deliver the information. Or that crucial error correction, completely unchanged to the deeper parts of the network.
And suddenly, that game of telephone stops being a fatal issue.
Precisely. Because of that one single modular tweak, that one new Lego brick, we went from 20 layers to networks that were hundreds or even thousands of layers deep.
That's when deep learning actually became deep.
Exactly.
Okay, so that's the foundation. We can build the tall towers now. Let's talk about the specific rooms inside those towers. The paper breaks these down into synergistic branches, Let's start with the eyes of AI, computer vision.
Right. Convolutional neural networks, or CNNs.
Now, we've had convolutions for a while, as we said, but the paper highlights this specific thing called the inception module.
Yeah. Inception.
Is this just a cool movie reference or what?
I mean, the name is, but it's really a philosophy. Before the Inception module, researchers had to make a hard choice. Do I use a small filter to look for really fine details like eyelashes? Or do I use a big filter to look for the overall shape of the face?
You couldn't do both.
No, you had to pick one specific filter size per layer.
And the inception module basically just said, why not both?
Exactly. It runs multiple different filter sizes in parallel, all within the exact same block, and then it stitches those results together at the end. It creates a much wider network that captures local detail and global context simultaneously.
That makes a lot of sense. The other vision block that really stood out to me in the review is MobileNet. It feels like this was driven purely by the smartphone era.
Oh, 100%. MobileNet introduced a concept called depth-wise separable convolutions.
Which is quite the mouthful.
It is. But if we break it down into plain English, instead of doing one massive computationally expensive mathematical calculation to process an image, it split the job into two smaller, much cheaper steps.
Which saves power.
Drastically. It reduced the computational cost so much that you could suddenly run complex facial recognition directly on a phone without draining the battery in 5 minutes.
Okay, so we have the eyes sorted out. But the absolute elephant in the room, the reason everyone on Earth is talking about AI right now, is the language block. The transformer.
Yes, the transformer. The paper frames this as the massive shift from recurrence to attention.
Let's unpack that for a second. Before transformers came along, we used RNNs, recurrent neural networks, like LSTMs. How did those work?
An RNN basically reads text exactly like you and I do, left to right, word by word. It processes the word the, then the word cat, then sat.
And it has to hold the memory of the previous word as it moves to the next one.
Right. It maintains a hidden state,
Hmm.
which seems perfectly logical. But it has two fatal flaws when it comes to scaling. One is memory. By the time an RNN gets to the end of a really long paragraph, it is almost completely forgotten what happened in the first sentence.
That vanishing gradient again.
Exactly. And the second flaw is speed. You physically cannot parallelize an RNN. You cannot process word number 50 until you have completely finished processing word number 49.
Enter the transformer.
Right. In 2017, the transformer stopped reading left to right. It looks at the entire sentence or even the entire document all at once. And that is driven by the self-attention mechanism.
The paper breaks attention down into three vectors: query, key, and value. And I feel like this is exactly where people's eyes tend to glaze over when reading AI papers, but it's actually a really elegant system.
It's essentially just a massive filing and retrieval system.
Mhm.
Imagine you are the neural network. You're trying to figure out the specific context of the word bank in a sentence.
Okay, I'm the word bank.
Right. You send out a query. It's basically a mathematical request asking the rest of the sentence, hey, who in here is related to me?
And everyone else answered.
Every other word holds up a key. It's essentially a label saying what kind of word they are. The network compares your query to all their keys.
So if I see the word river, that's a weak match.
Right, maybe a weak match in this context. But if you see the word deposit or money, that's a very strong match.
And that strong match triggers the value.
Yes, the value is the actual core information you absorb. Because the word bank matched strongly with the word money, you absorb that financial context. You, quote unquote, attend to those specific words, no matter how far apart they are in the text.
And the truly crazy thing here is that the model does this for every single word against every other word simultaneously.
That is the secret sauce. Because it's fully parallel, you aren't bottlenecked. You can throw the entire internet at it if you have enough GPUs. That modularity is directly how we scaled up to BERT, the GPT series, T5, you name it.
But, and this is a pretty massive but, in the source paper, the transformer actually isn't perfect. It has a fundamental flaw called quadratic complexity.
Yeah, that's the heavy price you pay for looking at everything at once. If you double the length of the text you're reading, the computational cost doesn't double, it quadruples. Yeah. It gets exponentially expensive to process really long things like entire books or massive code bases.
Which brings us to what the paper calls the new wave. These are fascinating new architectures that are actively trying to kill the transformer, or at least fix its major flaws. RWKV was the first one that jumped out at me, receptance-weighted key value.
RWKV is super fascinating because it's a hybrid approach. It tries to cheat the trade-off we just talked about. It uses time mixing and channel mixing modules so that it trains in parallel, exactly like a transformer. So it's incredibly fast to build.
But then when you actually use it,
When you use it for inference, it behaves like an old-school RNN.
so it doesn't actually need to keep the whole history in active memory?
No, it
Yeah.
rolls the memory forward linearly. It's incredibly efficient for really long, continuous conversations or for running on smaller, local hardware.
Then there's Mamba. I keep seeing Mamba pop up everywhere in the tech space. It uses something called state space models, or SSMs.
Mamba is the real heavy hitter in this new wave. It achieves true linear complexity.
Meaning the cost scales smoothly.
Exactly. You can feed it a sequence purely based on its length. We're talking millions of tokens, entire human genomes, and the memory cost does not explode.
Mhm.
If we genuinely want AI to analyze raw DNA sequences or write complete novels without losing the plot, Mamba is the architecture to watch.
There was one other really weird one, CANs. Kolmogorov-Arnold networks?
Oh, cans are a total paradigm shift.
The paper says they move the learnable functions from the nodes to the edges. What does that actually mean for the output?
Think about a standard neural network. The actual thinking, the weights, are locked inside the neurons themselves, the nodes. It's a complete black box.
Right.
In a can, the math happens on the wires connecting the nodes, the edges. The paper suggests this simple structural flip makes them vastly more interpretable and accurate for purely symbolic tasks.
Like heavy math, physics, discovering new formulas.
Right. So a standard transformer might just memorize the text E equals mc squared from reading Wikipedia, but a cane might be able to actually derive the formula from raw data.
That's the hope, yes. It provides a much clearer window for scientists to see how the network reached its conclusion.
Speaking of science and adaptability, we really have to mention liquid neural networks, LNNs. Honestly, these sound like something straight out of Terminator.
They do, but they're actually inspired by the brains of microscopic worms. The absolute key feature of an LNN is that it is time continuous.
Meaning what exactly?
Well, most AI today is frozen. You train a model, you lock in the weights, and you ship it out. If the real world changes unexpectedly, the AI fails.
It doesn't adapt.
Right. But an LNN adapts its parameters in real time as new data flows in.
So that would be perfect for, say, a self-driving car caught in a sudden rainstorm.
Exactly. It doesn't just blindly execute a pre-learned command. It adjusts its internal processing to the new slippery road conditions instantly. It's fluid, hence the name, liquid. I want to pivot over to the creative side for a minute. We've covered text and logic and self-driving cars. What about the Lego blocks for generating images? The paper tracks a really interesting evolution from GANs to diffusion models.
This is a textbook example of modular replacement in AI. For years, GANs, generative adversarial networks, were the absolute gold standard for images.
The classic forger and detective dynamic.
Right. You had two separate networks fighting each other. One generator tries to create a fake image, like a deepfake face, and the discriminator tries to spot the fake. They learn purely by competing. We got things like CycleGAN for turning horses into zebras and StyleGAN for hyper-realistic faces.
But they were notoriously unstable.
Very. It was incredibly hard to keep the game balanced. If the detective got too good too fast, the forger would just collapse and stop learning.
And then diffusion came along and just completely ate their lunch.
Diffusion works on a completely different physical principle, actually borrowed from thermodynamics. It's entirely about destruction and repair.
How?
You take a perfectly clear image and you slowly add static to it, Gaussian noise. You do this step by step, over and over, until the image is just pure random snow.
Okay.
Then you train the network to do one specific job. Reverse that exact process. How to take a slightly noisy image and clarify it by one step.
So when I sit down and ask Midjourney for a picture of a cyberpunk city, it actually starts with a frame of pure static and just hallucinates structure out of the chaos.
It denoises the chaos into the city, yes. It's a much more stable, controlled, step-by-step process than the warring GANs. And it's why it dominates high-fidelity images and audio right now.
There's one more crossover block the paper mentions that feels incredibly crucial for the hard sciences, PLNNs, physics-informed neural networks.
I love PNNs. This is the module where we finally stop trusting the training data blindly.
Because normally a neural net just looks for statistical patterns, right? It doesn't fundamentally know that gravity pulls things downward.
Exactly. If the raw data happens to say a ball floats up, the AI predicts the ball floats up. It has zero common sense. A PNN changes the underlying rules of the game. It bakes the actual laws of physics, like partial differential equations, directly into the loss function.
And the loss function is basically the teacher grading the AI's test, right?
Right. So in a PNN, if the AI generates a solution that happens to violate the conservation of energy, it gets hit with a massive mathematical penalty.
Yeah.
Even if the data looks perfectly right, if the physics is wrong, it fails.
That seems huge for structural engineering and material science.
It's revolutionary. It means you can simulate complex fluid dynamics or airplane wing stress with vastly less training data because the AI already knows the foundational laws of physics. It simply cannot hallucinate an impossible physical scenario.
Okay, so we've got this massive inventory of blocks now. We have vision blocks, attention blocks, physics blocks, liquid blocks. My biggest question is, how do we actually glue them all together? If I stack 1,000 of these layers, how do I keep the math from just exploding into infinity?
That brings us to what I call the vegetables of the review paper. The really unglamorous but absolutely essential stuff, normalization.
Things like batch normalization and layer normalization.
It sounds incredibly boring, but without it, deep learning just flat out doesn't work. Imagine you're trying to bake a really complex cake, but every single time you reach for an ingredient, your measuring cup randomly changes its size.
That would be a disaster.
That's exactly what happens inside a deep neural network. As the data moves forward through hundreds of layers, the numerical values shift and scale wildly. Normalization simply recenters everything at every single step. It keeps the data locked in a predictable range, usually between 0 and 1 or -1 and 1.
So the math stays stable.
Exactly. That, along with activation functions like RayLU, which acts as a simple on-off switch, or newer ones like GELU and Swish that are much smoother and used in modern LLMs, they form the glue.
The paper also talks heavily about transfer learning as a massive modular benefit. The Med3D example they gave was pretty striking to me.
This is the ultimate proof of the Lego thesis. Transfer learning means you almost never have to start from scratch anymore. You take a massive pre-trained block, like a 3D vision model trained on generic spatial data, and you just plug it straight into a specific medical application.
Yeah, they found that using a pre-trained block to look for things like lung or liver tumors improved accuracy by something like 3 to 20%.
Up to 20%, yes. But honestly, more importantly, it sped up the training process by 10 times compared to starting from zero.
10 times faster? That's incredible.
Think about what that actually means for a small local hospital or a university research lab. You don't need a $100 million supercomputer or millions of private patient scans to build a highly accurate diagnostic tool. You just need to fine-tune a generic module that Google or Meta already spent the money to build. It completely democratizes the technology.
However, the paper isn't just one big victory lap. It ends with a really sobering section on the challenges. And the first one is the double-edged sword of all this modular complexity. The black box problem is back.
We really have come full circle. We fully understand the individual Lego brick. We know exactly how a single attention head works down to the math. But when you snap a trillion of them together, the emergent behavior of the system becomes totally opaque.
We know how it processes data, but we don't know why it made a specific final decision.
Exactly. Why did the LLM decide to recommend that specific harmful book?
Mhm.
Or why did the vision model suddenly misclassify that benign tumor as malignant? In a massive modular system, the error could literally be anywhere.
The paper mentions topological data analysis, or TDA, as a way to map the geometric shape of the data flow inside the network.
Yeah, TDA is promising, but right now we're still largely just guessing from the outside.
Then there's this concept of catastrophic forgetting, which honestly sounds like a terrible medical condition.
It's a major limitation compared to biological brains. If you take a highly trained, chess-playing AI and you decide to teach it how to play poker using the same network, it almost always overwrites the chess modules. It completely forgets the old task to learn the new one.
Whereas humans stack knowledge. Learning how to play poker doesn't actively erase my memory of how the knight moves in chess.
Right. Biological brains have plasticity, the ability to learn, but also stability, the ability to retain. Modular AI really struggles to balance those two. Solving this is the absolute key to what they call open-world learning, building an AI that learns continuously from its environment without needing a complete factory reset every month.
And finally, we have to talk about the sheer physical cost, data hunger, and energy sustainability.
We are rapidly hitting hard physical limits on Earth. These large models are just ravenous for electricity.
Which is why the paper heavily emphasizes model lightweighting.
Right, techniques like distillation and pruning, just cutting out the useless modules. They also highlight spiking neural networks, or SNNs, which use special neuromorphic hardware that actually mimics the extreme energy efficiency of the human brain. We have to make the blocks dramatically more efficient, or we will literally run out of power grid capacity before we ever reach artificial general intelligence.
It really brings us back to the central theme of the whole paper. We aren't just magically birthing intelligence in a vat. We are painstakingly engineering it block by block, module by module.
And that engineering process is becoming highly empirical.
Ugh.
The paper describes the current state of AI research as a process of highly empirical modular experimentation.
Which is really just a polite academic way of saying trial and error, isn't it?
Pretty much, yeah. We're basically throwing an attention module over here, maybe a diffusion module over there, slap it on a reinforcement learning layer on top, and just seeing what sticks together without crashing.
That's the exact thought I want to leave everyone with today. We are getting really, really good at architectural collage. We can assemble these incredibly complex, beautiful mathematical puzzles. But if we are just throwing modules together to see what sticks, do we actually understand the intelligence we are building? Or are we just really good at architectural collage?
That is the multi-billion-dollar question. Are we true architects of cognition, or are we just advanced collage artists playing with blocks we barely comprehend?
And to take that one step further for you to mull over, if intelligence really is just an emergent property of stacking enough of the right modules together, what happens when this giant collage becomes complex enough to start designing and swapping out its own Lego blocks without asking us first? Do we even stay in the loop at that point?
Now, that is a slightly terrifying thought to end on.
Something to chew on for sure. Big thanks to the authors Wei, Wang, and Watada for this incredible roadmap. It's a dense paper, but it really clarifies the landscape of where AI actually is today. And thank you for breaking down the blocks with me.
Always a pleasure.
And thank you for joining us on this deep dive. We'll catch you on the next one.